Welcome to chapter 16, part 3. So we're now ready to fit our stochastic leverage model to the S&P 500 data. And this follows the same procedure that we've done in other case studies and demonstrations of iterative filtering. So I'll try to talk about some of the things maybe that are specific to this particular case. So we're going to use for a random walk standard deviation, this value 2%, that's 0.02 that we've been used in other situations and often seems to work well with a higher random walk perturbation for the initial value parameters. Remember the parameters that are only vary at time 0. And we're going to use a cooling fraction 50 of 0.5. That means over 50 iterations of searching, the random walk standard deviation gets multiplied by a factor of a half. That's roughly a 1% cooling, 1% decrease in random walk standard deviation for each iteration of the iterative filtering. Then we're just going to set up the random walk standard deviations according to these values. And we are going to set up a call to the iterative filtering, and so that's going to the key thing here is the call to MIF2, and we're going to use for each to do the parallel search, and then we're going to do some likelihood evaluations once we're done. This is pretty similar to what we've seen before. So this particular investigation took 20 minutes. This was at run level 3 on a cluster. And so we look at the points plot for what we get out. And one of the parameters we're most interested here for this particular question is whether the leverage is time varying, whether we gain by allowing the model to have a time varying leverage. Now, the random walk standard deviation on the leverage is sigma nu. It looks like the data want sigma nu to be pretty close to 0. Other things we might notice from this, the values of phi from this search. Phi is the autoregressive parameter for the stochastic volatility. This is in fact pretty close to 1. The volatility is not changing very quickly well, it's not autoregressing quickly, so it's essentially doing something close to the volatility, I guess, is doing something close to a random walk, and then it's not using the time varying leverage to as a feature in the model. Yeah, I think that's the main thing we get from this plot. So notice that we have cut off the log likelihoods by subsetting at a log likelihood of 20 below the largest we found, and that's basically to rule out any potentially there could be some searches that kind of failed, and we just don't want to see them in this plot. Anything that's more than 20 log units below the maximum is just not very competitive. Well, now we can do global maximization by starting random draws from a large box and repeating that many times until we're fairly confident that we have maximized, at least in the context of that box. And so here's the box that I used. And the call to MIF2 is very similar to the local search. And well, we end up with the well, let's look at the bottom for how the search has gone on. The maximum log likelihood was -3954. The lowest was -3996. That's really not so competitive, but at least half the searches were within 3 log units of the maximum. So it seems like there's a fair consensus that there's many points getting close to the maximum and we can't do much better. And sometimes the searches fail because it's a complex likelihood surface, reasonably high dimensional, and we're doing a Monte Carlo search. This search took 60 minutes on one compute node with 36 cores, and we have a maximized log likelihood. We're fairly confident that we can't do better. At least we tried quite hard and we couldn't find anything better. And then we can also look at the pairs plot again. What I've done here for sigma nu, we were quite interested in whether there's any evidence that it's non-zero. From when we just plotted sigma nu on a natural scale, the points were bunched up near 0. Now I've plotted on the log scale, and I think it becomes increasingly clear that sigma nu can get arbitrarily close towards 0. That's log sigma nu getting arbitrarily close towards -infinity without any penalty to the likelihood. And right, we also see on this there's some reasonable estimate of mu h, that is the long run average log volatility. And right there, that's the general pattern of the surface. And we certainly do not see evidence for sigma nu is greater than 0. It looks like sigma nu equals 0 may even be the MLE in this case. That may be Bretto found evidence for sigma nu greater than 0, but Bretto was looking at a longer subset of the data. So maybe over this shorter time frame, a constant leverage is just fine. You could compute a likelihood profile over sigma nu, but in this case, the kind of poor man's profile from looking at the scatter plot suggests I think you're quite unlikely to find curvature over sigma nu if you calculated that profile. Now, we've already calculated the likelihood by GARCH. It's interesting to think of the relationship between the GARCH likelihood and the stochastic volatility model. It has time-varying leverage, but in actual fact, our MLE essentially does not have time-varying leverage. It just has stochastic volatility model with leverage. That gave us a maximized log likelihood of -3954. The GARCH log likelihood was -4019. Well, GARCH has 3 parameters. We have 6, but that's quite a lot of likelihood advantage for the stochastic volatility model, and certainly AIC favors it. But you probably, this is 70 odd units of log likelihood. So that's really pretty strong evidence that this model is fitting better than GARCH. It also has extra interpretability for this it's a stochastic volatility model. You can see exactly how the volatility is evolving and how the leverage plays into it. But the GARCH model is still a useful benchmark because it's useful to know how your kind of more fancy mechanistic models compare with kind of simpler out-of-the-box alternatives. And the fact that we've beaten GARCH makes it fairly clear that we haven't screwed up too badly. We haven't accidentally fitted a really bad model. Actually, it seems like quite a good model in this case. It's when you try fitting mechanistic models, sometimes you beat simple statistical benchmarks, sometimes you don't. If you don't beat a simple benchmark, it doesn't necessarily mean that the mechanistic model is entirely useless, because you still have the interpretability. You can still learn from where the mechanistic model fails. Where the mechanistic model fails basically tells you what you didn't understand, and then you may be able to improve the model, subsequently beat the benchmarks. And even if you don't, you've learned something through the mechanistic modeling exercise. However, if your mechanistic model fits a whole lot worse than the benchmark, then you certainly need to rethink what you're doing. And so the benchmarks are an important sanity check. Well, the last thing we have is a little bit of algebra to go through the basically support the algorithm that we used, which was the variation on the particle filter. Well, to see how this works, it's helpful to think what is the proper weight for a general sequential Monte Carlo proposal. So when we do sequential Monte Carlo, we move our prediction particles according to the transition density of the latent marker process, f of xn given xn minus 1. Well, you could move them according to an arbitrary density q, but then you would have to reweight appropriately. And so what we have written here is how that reweighting works. So the proper weight is the measurement density times the ratio of the transition density to the proposal density. And when we do the basic particle filter, we choose Qn to be fxn given xn minus 1. And so the numerator and denominator cancel, and the proper weight is just the measurement density. And that's really nice. You can think of this as explaining where the plug and play property comes from, because fxn given xn minus 1 is something that we may not know. We may not be able to evaluate it. We can simulate from it. And so it's really nice to set this up so that those things cancel, and then we don't have to evaluate the transition density. But here, we're playing a slightly different game, because we are going to suppose that the state has these two parts, un and vn, and our measurement model depends only on vn. So there's a part un that's entirely unmeasured. And we're going to make a proposal for which un, the un part, is the plug and play transition density f of un given xn minus 1, and the other part could be anything else. We're going to call it gn of vn. And so it's partially plug and play because only part of it is drawn from the simulator. The vn part doesn't have to be. If you when you use that proposal, that part of the numerator and denominator cancel. You can factorize the numerator and denominator in the same way, and the u part cancels, and you just have the v part left over. And so on the numerator, you get f of vn given un xn minus 1. And on the bottom, you get gn of vn. That's just whatever proposal distribution that you had before. And then we decided that the measurement should only depend on vn. So you still have f of yn given vn there. Now, we're interested in the case where vn is the thing that's perfectly observed. So we're going to set yn equals vn in the case of our stochastic volatility model. And then the density of yn given vn is formally a delta function, because that's basically an infinitely peak density at yn equals vn. And it makes sense to choose GN. GN's allowed to depend on the data, right? When you have a proposal distribution, it's allowed to depend on the data. And we can use GN to exactly make this cancel out nicely. So GN is going to put a mass on Vn being equal to the data yn star. And then when you look at that previous slide and you see what's left for the proper weight is the density of yn given un and xn minus 1. And that turns out to be what we use in our POMP model. And so everything's cool, and we do get a we get a proper estimate of the likelihood function via the particle filter, just using this slightly different factorization. And that's the end of chapter 16.